Hello and welcome to the SAR ADC design project for phase 2. This is the team of Nitin Babu and Rupesh. So first, I would like to talk about what was done in phase 1. We designed a switch capacitive amplifier and then we designed the OTA. In this phase, we are going to explain the design of the CDAC and the SAR ADC. So all these components together will form the pipeline SAR ADC. Before we start making the SAR ADC, we need to make certain building blocks which comprise the design of the ADC. So they include the comparator, the NOT gate, the NAND gate, the NOR gate, and the flip-flop. For the comparator, we use the strong arm latch topology and the circuit is shown on the screen on the right side. We use the sizing as described and then we test the comparator using a test bench to verify its working. Next, we will look at the NOT gate. So we use the simple MOSFET design of an inverter to design the NOT gate, and we use the minimum sizing. So we set L equal to L min, and for the NMOS, we set W over L equal to 5, and for PMOS, we set W over L equal to 10. Similar to the NOT gate, we also designed the NAND gate using MOSFETs, PMOS and NMOS using the simple NAND gate design, and we also set sizing accordingly. Again, like we did for the NOT and NAND gate, we also designed the NOR gate. And finally, using multiple NAND gates, we designed the flip-flop, which also includes both the set and reset operations, which are falling edge triggered. And the sizing of the flip-flop depends on the sizing of the NAND gate, which is the minimum sizing. Now we will look into the SAR ADC design. We opted to choose for the conventional switching scheme as opposed to the VCM based switching scheme, and the reasons for that is because in this scheme we will have lesser number of switches. It is also very easy to implement the circuit, and the circuit is also very simple. Next, we have to look into the timing scheme. We are given a constraint of a frequency of 50 megahertz. 50 megahertz is equivalent of 20 nanoseconds time period. Out of the 20 nanoseconds, we will run a counter, a 10-bit counter. So each bit will take 2 nanoseconds. Among that, the first 8 nanoseconds is given for sampling of the input, and the next 12 nanoseconds is for converting each bit from the MSB to the LSB. Now you can see the SAR topology on the screen. We have a CDAC, we have the SAR logic, and we have the comparator. And this is the simple SAR topology that we are using. For the CDAC design, we will use 3 switches at each capacitor for the input, for VREF, and to connect to ground. And this is the basic CDAC design. And we choose CU to be 12.5 femtofarad, so that 64 times CU, which is equal to the total capacitance, is equal to CS from the phase 1 design of the switch capacitive amplifier. Now we look at the SAR logic design. We use the simple design of a 10-bit counter, and then at the bottom you could see the flip-flops whose output is the digital bits, and when the start signal is high, then the SAR logic will start the operation. So once we get the bits from the SAR logic design, we need to use that to give the inputs to the CDAC switches. So on the screen you could see the logic that we use for each switch in the CDAC. Now that we have everything ready of the CDAC and the SAR logic, we will simulate the circuit. So first you can see the timing diagram. On the top, the 2 signals are the V in P and V in N, which is the input analog waveforms. And on the bottom, you could see the input differential voltage versus the output digital voltage converted to an ADC voltage. And we can see that the SAR ADC conversion is happening fine. Now we will look into the timing diagram of the SAR logic of the S bits, and we see that the circuit is working fine. So this is a zoomed in circuit over three time periods. And next we will look into the waveform of the bits, and finally we will look into the DFT plot. So the SNR right now is 37.01 dB, which has an expected number of bits of 5.9 bits, which is very close to 6. So we can say that our circuit is working fine. Until now, in our design, we used ideal switches. But now we need to design switches using MOSFETs. So first we will look at the NMOS switch, which is used to connect a node to the ground. We use the sizing as mentioned on the screen, and this sizing is only for the base case. So if we are connecting the switch to a capacitor Cu, we use this size. And if we are connecting this switch to a capacitor of size 16 Cu, then we will multiply the width by 16. So we are scaling our switch proportionately. The PMOS switch is used to connect a node to VDD or VREF. And similarly, in this case, the sizing will scale based on the capacitor the switch is being connected to. Next, we will use a transmission gate switch, which is used to connect a node to VCM. So this consists of an NMOS and a PMOS in parallel, and the sizing is similar to the NMOS and PMOS switch. Finally, we will look at the bootstrap switch, which is a bit more complicated than the switches we looked before. This is used to connect a node to Vin, which is a voltage that can vary from 0 to VDD. The sizing of this bootstrap switch is a bit complicated. The main NMOS in this switch will have a sizing of Wn equal to 250 nanometer and Ln equal to 50 nanometer, and this will scale similar to the capacitor it's being connected to, like in the earlier cases of the transmission switch, PMOS switch and NMOS switch. The other NMOS and PMOS in the bootstrap switch will have a fixed sizing as mentioned, and the sampling capacitor Cs is of 1 picofarad capacitance. Finally, after designing the switch, we again simulate the circuit, and the timing diagram now looks similar to before. We can see that the average power of the circuit is 1.68 milliwatt, which is slightly higher than the 1 milliwatt constraint, but at least now we have a good working circuit and we can later try to reduce the power. The timing diagram of the S counter is the same as before, and the bits also seem to be working fine and equal to the case when we used ideal switches. And finally, the DFT has slightly worsened when we use the real switches, but it is still really high, and the expected number of bits is 5.6, which is still a good number. So we are at a good point right now. So to conclude, we have completed the design of the CDAC and the SAR logic, and we have also designed the real switches and ensured that the working of the SAR ADC is good. We also ensure that the circuit has a good SNR even after using the real switches. So in the future work, we need to reduce the power consumption of the SAR ADC. We have to analyze the reason why we are having such a high power and then take steps to reduce that. Later, we will also integrate the ADC that we have designed in the SAR ADC pipeline and make sure the pipeline works. And we will also use the switches that we have designed right now in the switch capacitive amplifier, because earlier in phase 1 we used only ideal switches in the switch capacitive amplifier, and now we will use these switches over there, and we will do all this work in phase 3. Thank you.